You are listening to 95.7 FM WELT, Fort Wayne, Radioactive. The opinions and views expressed in the show are those of the hosts and guests only. They do not represent those of FreeThought Fort Wayne, WELT, or any other organization. Welcome to the Hoosier Humanist Hour, where we explore science, religion, culture, ethics, and community from the humanist perspective. Join us as we discuss those topics and more, free from the ideologies of religion and superstition.
Good evening, and thank you for joining us for another episode of the Hoosier Humanist Hour. The Hoosier Humanist Hour is a show dedicated to discussions on all things humanism, and really just about anything, so long as we can discuss it from the humanist perspective. The Hoosier Humanist Hour is brought to you by volunteers from FreeThought Fort Wayne in association with the American Humanist Association. My name's Caleb. I'm joined today by Rex and V, as well as our technical advisor, Andrew. And our topic for today, I thought this would be kind of fun, guys. Today's topic is the universe beginning to end, theories and misconceptions. Really, one of the main reasons why I chose this particular topic for the week is I really wanted to quell common misconceptions about the scientific explanations for the birth of the universe, its formation, and its death, particularly amongst the most fundamental of religious folk. I can't speak for all. Most of the fundamentals that I talk to are Catholics, specifically, and they have a very skewed view of the science behind pretty much anything. Honestly, it doesn't even have to stick to astrophysics. I mean, their view of science is just bizarre to me. But we'll get into that a little bit later. And I also really want to try and discuss and explain how we can know that science is an accurate and reliable means for acquiring knowledge. And luckily for us, we just happen to have a biologist with us today, Rex. I actually just kind of want to ask you, since you're the only one here, I believe, hopefully I don't offend anybody, who's an actual scientist. I thought it'd be appropriate if you went ahead and tried to define science as best you can, and why and how we can know that science is a reliable means to come to conclusions about reality.
First and foremost, the scientific method is what really is the foundation of all science, and people tend to treat it like this magical, weird thing that they have no clue about, even though they utilize the scientific method on a daily basis. You know, if they experience a poor result from an action that they do within the day, they tend to avoid doing that action again. You know, if you put your hand on a hot stove, you tend to avoid ever doing that again. That's the scientific method. Now, obviously, in the scientific method, we tend to want to test something repeatedly to make sure that we get the same result over time. We also want to control for as many variables as possible, but scientific method by itself is fundamentally one of the pieces of logic and reason that we use on a daily basis. And so it's very frustrating when we see instances of people not necessarily utilizing the scientific method in all aspects of their lives, which is really what the scientific method is meant to do. And as such, we can also consider different levels of confidence in the results that we get while doing science using the scientific method, which is to say, doing something once and getting a result isn't terribly meaningful until we do it again and again and again, thousands of times over. That's when it starts to become meaningful.
Okay. So would you say that it would be fair to say that the proper skeptic should be using the scientific method for pretty much everything that they do?
Right. Now, the caveat behind that is that what I'm talking about is experimental science. There is a difference between experimental science and historical science. Those are two different things. However, they do still require a mountain of evidence supporting something, a particular hypothesis or whatnot.
Oh, well, I'm actually really glad you said that. So I kind of want to ask then, do you believe, or is it true then, that when we look into Big Bang cosmology, that is historical science?
Well, with the Big Bang, absolutely, it's a way of looking at clues from the past in order to try to piece together what happened. So yes, it is historical science because in a laboratory we can't necessarily recreate the Big Bang, but we can certainly prove a number of the principles that underlie the Big Bang.
Well, let me just interject something here real quick. I mean, it is, Chris, you're absolutely correct in what you're saying. Um, but, astronomers, when they look at stars that are really, really far away, they actually see those stars as they were in the past. Or, if they look at an object that's, let's say, a billion light years away, they look at that object as it was a billion years ago. So, scientists also have, ways to look back in time, not anywhere near uh, the moment of the Big Bang. There's just no way to see that. Um, but we have ways to get pretty close to it, as cosmologists do anyway. And scientists try to recreate the conditions that existed back then in various laboratories. So it's kind of a mixture of historical and science that you can do right now in the moment, kind of thing, and it gives you information, direct observation, even of how things were uh, back at that time.
That kind of reminds me, I don't know if you guys ever saw the Bill Nye versus Ken Ham debate over creationism versus naturalism, I suppose. And Bill Nye ended up crushing, as far as I'm concerned, creationism in a single quote. He illuminated the fact for me that you can just look up at the night sky and see stars and galaxies with your naked eye that are more than 10,000 light years away. At that point, it's simple math. You could figure out just by that alone that the universe has to be more than 10,000 years old. Otherwise, that light wouldn't have reached us yet. And because of that as well, like you were saying, it's essentially us looking into the past in real time, in a sense, because time is relative. But this is good. I actually like this. This really transitions us into where we really want to go with this. What I really want to ponder on tonight is using proper skepticism when trying to ask and find the answers to the big questions, such as why is there something rather than nothing? A lot of people, I think, tend to phrase this question in a weird way, which creates this sort of internal bias to think that there's a creator. Like, for example, let me just say what I'm trying to say here. A lot of Christians, for example, or people who are religious in general, they will say that the universe was created at such and such time. But obviously the word created implies a creator, hence why they think it's more likely that a God would have created the universe than that it would have come about by natural means. And I think that it's really important to really emphasize how skeptical we should be about any claim that tries to answer that sort of question. Where did the universe come from? Why is there something rather than nothing? There was a quote from Neil deGrasse Tyson that I love that I posted on our Facebook page the other day. And I believe it went something along the lines of where data is sparse, ideas abound that are both clever and wishful. Essentially what this means is when we don't really have that much data, people tend to just make crap up that sounds and feels good to them. And if they find out and about in their research information or data that even kind of suggests that their ideas are correct, then they'll really cling on to that and accept that as fact. And but anyway, I really want to kind of just point out the fact that humans in general have a desire to understand the cosmos. And we go through a lot of different channels to try and figure that out. Historically, we've tried a lot of different methods to try and answer these questions. I think that the first real attempt to try to answer these questions came from religion. But eventually, religion in these regards generally got replaced by science.
Let me jump in a little bit here. So one of the things that I wanted to mention, Caleb, while you were talking about all of this, is oftentimes, people even ask the wrong question. Oftentimes people ask, why is there something rather than nothing? And the why question, really implies some kind of purpose, some kind of design. Like, it's an improper question. What the proper question should be is, how did we arrive at this state of the universe where there is matter, where there's light, where there's stars, where there's big space, where the fundamental forces of the universe are the way they are? How did we arrive to this point where, for example, gravity is so much weaker than electromagnetism? How do we arrive at the state where the nuclear forces act on these very, very short distances, and electromagnetism acts on these very large distances? So really the question of why might be an improper question. And also, oftentimes, it was religious people, well, not oftentimes, but in some cases it was religious people that have moved the science, in the right direction. If the religion you subscribe to is not so dogmatic as to prevent you from actually exploring the formation of the universe, from exploring the physical laws and all that, you can actually make scientific progress and be a religious person. I mean, a great example is a guy by the name of George Lemaitre, who actually came up with the theory of the Big Bang. And he was a Catholic priest in I think it was 1933 or something like that, when he, or I think it was in the late 1920s actually, when he came up with his theory of the Big Bang based on the general and special relativity laws that Einstein had come up with. He basically just, worked those back in time and figured out that the universe must have started in this tiny, tiny little dot. I mean, at the time, Einstein believed that the universe was this static universe where things didn't change from day to day. There was the same number of stars today as there was yesterday, like all this kind of stuff, right? So at the time, in the late 1920s, scientists generally believed in a static universe. And here's this guy, this priest, George Lemaitre, that comes around and says, no, it actually started at a point and it expanded really fast, and so on. So I guess it kind of depends on how dogmatic your religion is in a way.
Well, sure. I mean, I get what you're saying. I honestly, I agree. I think that properly motivated, it doesn't really matter what your religious background or irreligious background is. I think properly motivated, the right person can get those answers. It's been proven time and time again. I think the vast majority of scientists throughout history have been religious. And, that doesn't validate the claims of their religion. But it just means that they can still maintain those beliefs and make these amazing discoveries and be able to show their work for it too. What you were saying really got me thinking about Hubble when he discovered that, because, in my mind, I'm thinking one of the best ways to figure out whether or not something is likely to be true or not is to obviously try to find as many lines of evidence as possible that lead to the same conclusion. And Hubble, when he looked up, he ended up realizing that stars that are 3 times as far away as the nearby stars seem to be moving 3 times faster. And this growth was very consistent. And what he ended up showing through it's a very complex process back then. It's a little easier to grasp now, but long story short, essentially he just measured the shift in the wavelength of light to figure out whether or not a galaxy was moving towards or away from us, and then also to use that light, the measurement of that light, to figure out how quickly they were moving from us or towards us. And what he ended up finding is that the vast majority of celestial bodies are moving away from us out there, and this is happening everywhere. And that the longer this process goes on, the faster it goes. And we'll get into the implications of that later on down the line, I'm sure. But what that essentially meant is if you played the clock backwards, eventually the universe had to begin somewhere at some time. At least the universe as we know it. And that's an important little note to add in there, a little footnote. Because the universe as we know it had to have begun at some point if it's expanding faster and faster. The reason for that is as the universe expands faster and faster, eventually the universe itself is going to look quite different. So in other words, that would mean that the universe that we live in is not a static universe. The universe is going to change, and therefore the universe likely has already changed. And we have this evidence to suggest that the universe began at some point. And then, like you were saying, that pastor, I forgot his name.
Yeah, the
George
guy's name
Lemaitre.
was George Lemaitre.
Yeah. Yeah, he proposed it. I think that Hubble was one of the first, if not the first, to really validate that in any real sense. And then you get all the way up to the folk that were trying to, or excuse me, not trying to. This happened by complete accident. A group of scientists that were pointing antennas up in the sky looking for microwaves, and they ended up discovering the background microwave radiation on sheer accident. They weren't really looking for it, but it happened. And so we can actually look at a snapshot of what the universe looked like when it was approximately 380,000 years old, if we wanted, using this data. And we can get into how we know that that's how old the universe, or how we can be sure that the universe was approximately 380,000 years old when this photo, quote unquote, photo was taken. And the thing that I really want to emphasize, and we kind of want to hit the pause button before we get too deep on a lot of this stuff, is that a lot of this is highly speculative. And even if a lot of this is true, there are a lot of potential implications for what that insert here could be. Which is why, again, I really want to emphasize how important it is to be properly skeptical of all of these sort of claims. Now, you can believe that nothing can come from nothing, and that something cannot. And therefore, God had to do it. You can make that leap, but do you have good reason to make that leap? You have to come to a conclusion that is most likely based on the data. And if there's absolutely no data to suggest a correlation aside from your opinion, then you should probably take a step back and think to yourself that, okay, maybe this really isn't the case. So anyway, I'm sorry that was a little pedantic, I suppose.
No,
but
that was really good, because honestly, that was the exact conversation I just had with a bunch of religious protesters at Gay Pride a few days ago. There were two Christian groups, just like there were last year, protesting the Gay Pride March and Gay Pride Festival here recently in Fort Wayne. And it was great being able to talk with them and being on TV with footage of me talking with these people, because they at no point delivered any data to me. All they did was deliver their beliefs which are unfounded on anything except the content within a single book. Which is to say, they might as well have just told me that Beauty and the Beast was a real thing because they read the Beauty and the Beast book by Disney.
Let me throw in a couple of interesting things in there as well. We were talking about Hubble and some things that he discovered, but I think it may be interesting to to say, how he actually discovered some of this stuff and what were his discoveries, just to kind of show that, he didn't just look at these stars and decide how far they must be. Like, he didn't just, make these numbers up. I mean, the instrument that Hubble was using in the 1920s was a telescope with a reflector that was 100 inches wide. I mean, this is a huge, huge telescope. Okay, it was on top of Mount Wilson in California. And what he was looking at was, these, what they called at the time, nebula, which literally translates as a fuzzy thing. See, back in the time of Hubble, they didn't even know that there were other galaxies. Like, people thought that the Milky Way was the only galaxy out there.
Yeah, right? That's another reason why they thought, another one of the reasons why they thought that we lived in a static universe as well.
Yeah, precisely. But what Hubble discovered was looking at the, what we now know is the Andromeda Galaxy. He then thought it was the Andromeda Nebula, and it was maybe just a little bit of dust or something like that was in there. But he found these variable stars in there. They're called Cepheids. And the cool thing about these variable stars is their brightness changes with a certain frequency. Okay, so their brightness goes up and down and up and down. Well, the speed at which that brightness changes relates to their maximum brightness. So if you know how bright you perceive them, and you know how fast their brightness is changing, means that you know what the maximum brightness is. All that information allows you to calculate how far away that star is. And what Hubble calculated is that that star couldn't possibly be inside the Milky Way. I mean, they knew how far away the farthest stars in the Milky Way are at that time. So in these stars, these Cepheids, as they're called, I believe that's the proper way to pronounce them, were too far. And, that kind of turned the scientific community in astronomy on its head. I mean, all of a sudden there were other galaxies. And soon, they found many, many of these things. All these nebulae that they'd seen before were now all of a sudden giant galaxy, each one with, maybe hundreds of billions of stars in it. So it completely turned upside down the whole field of astronomy. So, Caleb, the reason why I kind of wanted to mention the telescope in there is because you just kind of mentioned that he looked up. He looked up with some serious.
Oh, yeah.
I mean, it's 100-inch telescope.
Oh, absolutely. I don't want to downplay the engineering alone. Actually, to create this mirror, they used I believe it was mercury. If not mercury, it was some other metal that has a relatively low melting point. And they took this big bowed vat, kind of shaped like an umbrella, that's upside down. And they put the metal in that and just spun it slowly at a very consistent speed. And then once they got it to be spinning at that very consistent speed, then they cooled it down. And that's how they ended up creating the mirror for that, because they didn't have a means to make a mirror that was that big at the time. There would always be imperfections in the mirror, and when you're trying to use precision equipment, obviously you can't have that. So they had a whole new method of making mirrors just for this. So yeah, absolutely, I don't mean to downplay it. It's just, there's so much to talk about when discussing the beginning of the universe and its formation and such.
Well, the issue that I had with the religious people, I was just saying that the biggest issue that I had with the religious people was when I sat them down to talk about, well, how can something come from nothing? And so I asked them outright, I was like, well, do you happen to know anything about quantum physics? And of course, the answer to every question whenever I asked them if they knew any science was always no, which is astounding that they think they can talk about something without actually knowing anything about it. But so I asked them this question, they said no, and I proceeded to teach them about quantum physics and basically explain on a fundamental level how a particle can come from nothing. Needless to say, it just went right over their heads, and they just ignored me and proceeded with the rest of their arguments. So it's astounding how when you break down quantum physics and when you discuss how a particle and an antiparticle can spontaneously arrive out of empty space, it just blows people's minds because they really don't understand how unpredictable the realm of quantum physics is. But the thing is that when you total up all of the energy and all the particles in the universe, we still get an equation that totals up to 0. So the universe actually is nothing. It's just nothing split into clumps of something and nothing. An anti-something, I should say.
Well, sure. And, there's actually a lot of different, well, maybe a lot. There's at least a handful of interpretations of this thing. Like, for example, that could potentially mean or be evidence towards the fact that we live in a holographic universe, for example. That none of this is really here. That this is, in a very real sense, a sort of hologram. I like where you were going with this because I believe, correct me if I'm wrong, but I believe what you're essentially describing is how Lawrence Krauss describes a universe coming from nothing. Is that right?
Not familiar with his work.
Oh, okay. Well, I highly recommend it. I'm not saying that he's correct on this, but he's extremely convincing. And he's saying what you were saying there. That remember what you just said there. They asked you, how could something come from nothing? And he's a astrophysicist, a theoretical physicist, and a particle physicist. And he's said, okay, let's try and figure that out. Let's ask the question. So he spent his entire life trying to answer this question. And what you just described is exactly the way that he describes how our universe came from nothing. And what he means by nothing, and this is very important, is there was no universe, there was no space, no time, there was no universe, and then there was a universe. Okay, that's how he describes it. And what he says, I'll try to put this in a nutshell, but this is very complex work. The way that he describes it is that if you have a state of nothing, that is actually still a physical state. Something is a physical state and nothing is a physical state. It's the absence of a physical state, which describes a physical state. So what he's saying here is that nothing, with no space, no time, nothing there, is extremely unstable and will eventually become something because of something that operates in the realm of quantum mechanics known as virtual particles. Virtual particles aren't technically real particles per se, but they have very real potential. And one way to kind of nutshell how all this makes sense when we're talking about how a universe comes from nothing is to ask the question, was there potential for a universe to exist? Obviously, the answer is yes. Even if you answer that question no, then what you're saying is that there was no potential universe for God to create, if you want to believe that God created the universe. So you even counter your own God argument there. So you have to, at the bare minimum, unless you are a hard solipsist, you have to admit that obviously there was potential for this universe to exist. Otherwise, we wouldn't be here. That's kind of one way to nutshell it. I don't think I've ever heard of really simple explanation of what's going on here. This is stuff that you will have to do some research on your own for. But if we had a state of total nothing, and in this state of quantum nothing, virtual particles come in and out of existence, it would and will eventually happen, actually. It's inevitable. At some point, something will be left behind because of how these virtual particles behave. Mind you, all of this also, okay, I'm going to take a step back and pause. Again, with this skepticism here, this is very important because none of this has really been verified, mostly due to the fact that we don't have what's called a theory of quantum gravity. Because in order to suggest that virtual particles could create a universe, you would have to suggest that once these virtual particles create a particle and its counterpart, quantum gravity would interact with those parts in some way that on occasion, approximately 1 in 1 billion pairs, one of those interactions won't immediately annihilate each other. Because that's what happens when virtual particles create things. They almost instantaneously cease to exist. They annihilate each other. So this is one of Heisenberg's principles, that so long as you don't have enough time as an observer to measure the thing that the virtual particles are creating, then it can still exist for that brief moment, for less time than the observer can observe. In other words, you can't actually observe the thing. It's according to Heisenberg, it's impossible. Because every once in a great while, due to the quantum gravity, assuming quantum gravity is even a thing, then at some point, a very real particle will come into existence, like a photon or an electron or something, quarks, these sorts of things, bosons. Those things can come into being. And what Lawrence Krauss suggests happened is that if you wait long enough, eventually even whole universes will come into existence. Now, most of these universes will self-annihilate, just like the 1 in 100, like the vast majority of the virtual particles that create things. The vast majority of those things will self-annihilate. But every once in a while, one will survive. So the way that Lawrence Krauss describes this is that there's a sort of cosmic natural selection taking place, wherein universes come into being all the time, but they just annihilate themselves almost immediately. But every once in a while, one doesn't, and it survives and it thrives. And the ones that can have observers like ours can look up and contemplate how the universe came about, and the ones that don't have observers don't, and nobody will ever know that they exist. Any thoughts on that?
Let me throw something else in there. We talk a lot about virtual particles to give examples of something coming from nothing. And there's actually much simpler example of something coming, something that is created that didn't exist before. And it's as simple as photons. The reason why things shine is because electrons, that move around an atom, move from one orbit to another. When they do that, there's a photon that's being emitted or absorbed. If they move from a higher orbit to a lower orbit, a photon is being emitted. That photon did not exist, okay? It literally showed up out of nowhere. The electron lost a little bit of energy, but the electron is still there. Every other particle is still there. And that photon just appeared out of nothing. Another example, just to explain to people why we know for a fact that these virtual particles exist, is the weight of a proton. If you take the weights of the little particles that make up the proton and you weigh those don't weigh enough to make the weight that we know that the proton has. So it's the virtual particles that get generated inside of the proton itself that give it that extra mass to make it as massive as we normally measure it. And kind of just to kind of throw something else in there that you were talking about earlier, these virtual particles that come in and out of existence, as long as they don't exist for a long enough period of time that we can measure them, they can exist and they can be anything. And I've heard Lawrence Krauss describe this as, if you can't measure it, anything goes. If those virtual particles only exist for a small enough amount of time where they cannot be measured, they can exist in any way, shape, or form. Almost.
Yeah. Well, yeah, absolutely. I agree. Even if I disagreed, I'm not properly qualified to say that it's wrong.
Yeah, none of us here is scientists. We're just kind of talking about stuff that we've read and then we've researched, and hopefully, at least in my opinion, I hope that this show sparks some interest in people to go and research this stuff on their own. I mean, we can throw some data out there. We can throw some of the stuff that we've learned. We can push some names here and there of people that may be interesting for some of our listeners to know about. But none of us are really physicists or anything like that.
If I could say something real quick, just to build upon what V just said, you're mentioning a photon coming out of nothing, essentially. But don't we don't we have a mass on the photon?
No, the photons are massless. The electrons have mass, but photons are massless. It's actually even weirder than that. Um, when electrons move between orbits, it's as if they don't transition the space from one orbit to another. It's as if they literally were in one orbit and then they're in another orbit with no, they couldn't have moved slowly from one orbit to another, or the photons wouldn't come out the way they come out with these discrete energies and, like nicely, tightly packaged as a particle.
Well, I'm probably mistaken on this, but I'm pretty sure that photons carry an arbitrarily small amount of very real energy. And I mean, for example, you can know this because they at the very least have kinetic energy on some level. For example, the city of Chicago is 300 pounds heavier on a sunny day than it is at night.
Photons carry energy, but they don't have mass. And part of the way we can know this is people want to build solar sails where they want to send these spacecraft out in space where they're going to inflate this sail just like on a sailboat, and the photons from the sun are going to hit the sail and are going to move it. So photons have energy, they just don't have mass. It's kind of weird. I know, at least how I understand it.
But I guess the overall point that I was trying to get at was that, it is energy, which is to say, it doesn't necessarily come out of nothing. It does come from energy, and it's the energy that is lost as an electron goes down in orbital.
Right. But that photon wasn't like, okay, when you take a proton, you can split the proton into quarks. You can take a neutron and split it into a proton, and an electron, and I think a neutrino or something else. All these other, but the electron is an elementary particle. It cannot be split into anything else. So that photon, it's not like it was inside the electron, just kind of hiding in there as another quark or something. So the way I've heard of it described is it literally just popped up.
Well, I have another example.
It still follows the laws of physics, is what I'm saying. Because
it follows
the fact
conservation of energy, all that.
Right.
Yeah,
so it doesn't necessarily appear from nothing. It is a manifestation of the energy.
Right. But that particle wasn't there. So anyways.
But according to you, it wasn't a particle, though.
Yeah,
it's a manifestation of energy.
Yes.
Right. Well, what if we make an analogy that was an actual particle? Would you agree, Chris, that quantum tunneling, for example, is in and of itself a state of something coming from nothing? You have the alpha particle from the inside of a uranium atom that ceases to exist for a moment and then reappears on the other side of that molecule and gets ejected that way through the process of quantum tunneling. Would you say that is something coming from nothing?
Well, I really feel like that's just a product of quantum physics. Like that's not surprising to anyone knowledgeable about quantum physics, because the fact that quantum physics doesn't necessarily deal with solid objects where we can track their movement and position simultaneously. That's not what we're talking about in quantum physics. We're talking about a world where you can either know where something is or know where it's going, but never both.
Yeah.
Let me just explain. You brought a very interesting phenomena here that is quantum tunneling, and probably nobody out there knows what quantum tunneling is. So imagine you have this particle, and this particle is moving, so it has some energy, and it's about to hit a wall. And the energy level on the other side, or maybe not so much a wall, but it has to hit a mountain, right? And it doesn't have enough energy to go over this mountain. But the energy level on the other side of that mountain is lower. It is low enough where that particle could potentially go there if that mountain wasn't in place. And so what quantum tunneling means is that every once in a while, that particle would just appear on the other side of this mountain. Now, normally the mountain is just some kind of energy barrier. It may be an electric field or a magnetic field, an electron being blocked by some electric field or being repelled by other electrons. But if that electron could go on the other side of that boundary, and if the energy stayed there is low enough where the electron could normally go there, should that boundary not be there, it'll every once in a while just appear on the other side. It's incredible that even happens. But actually, if it didn't happen, the sun wouldn't work. The temperatures inside of the sun aren't hot enough, apparently, and the pressures for the sun to continue working if quantum tunneling wasn't a real thing. So
All right.
go figure, craziness.
And yeah, and again, I want to emphasize, out there for anyone who's listening to this that thinks that, oh, well, quantum tunneling sounds like just something that some people kind of think might be the case. No, this stuff is very well understood. I mean, we've known about quantum tunneling for some time. I mean, that's how most fire alarms work. There's a little piece of uranium in there. When an alpha particle is created because of the contact from smoke or certain chemicals, the process of quantum tunneling occurs, and we measure this, and that's what sets off the alarm. And, this is, radiation. And so obviously we knew about these sorts of things during the Manhattan Project. So, I mean, these things are very well understood. I just really want to throw that out there because I when I talk to people,
there's another thing. Let me just throw this in there real quick. I just want to throw something else in there very, very, very quickly. There is anybody out there can go and buy themselves a tunnel diode, and it's an electrical component. It probably costs you $1, and its workings depend on quantum tunneling. So semiconductors that are the basis for electronics that we use today, some of them depend on quantum tunneling, that very effect, or they wouldn't work the way they work. So it's a very real effect. It's not something that we made up, and you can go and buy a tunnel diode for a couple bucks and a voltmeter basically, and you can verify there's some weird properties of these tunnel diodes that will only work if the tunneling effect works. So you can verify that in your own home lab for with $20 worth of parts and measurement equipment.
Yeah, well, you're absolutely right. And one of the perspectives that I get a lot of is the Catholic perspective on this stuff. Catholics have a very real fear of science. Just ask around. And when you explain these sorts of phenomena to them, they just, in their minds, it's so absurd. It sounds crazy. If you don't know anything about science, it sounds crazy. And I just want to emphasize the fact that, just one last time, we understand these processes very well. We've done a lot of research. We, scientists and researchers, have done a lot of science research into this over the last 100 years or so. Look into it. I assure you, it's pretty convincing. This is why I can believe some of the weirder versions of what morality might be. I can really believe that the universe came from nothing. That is so counterintuitive. Really, it really is, to think that something can come from nothing. But I can, I didn't believe that not too long ago, but I've done quite a bit of research into this. I've invested quite a bit of time into this, and I'm convinced that it's at least possible based on the evidence. And the fact that it's at least possible means that it's more likely than some supernatural explanation like a God did it. I'm sorry, that's the end of my rant, Chris.
Oh, I was just going to relate it to a biological example, because a lot of the examples that we've been bringing up are either mundane or related to machines or other abiotic factors, and that doesn't connect with people very well. So what I like to bring up is a biological example of this quantum phenomenon, where we're essentially getting at the notion that in the quantum realm, if a particle finds a way to do something, and to do something most efficiently, it will somehow find a way to do it, this subatomic particle. And we can see that in some of the organisms, the photosynthetic organisms that live deep in the ocean, or at least much deeper than let's say 100 feet, where there's very little sunlight, and it's very, very difficult for them to survive as photosynthetic organisms, because you kind of need light to do that. And in these organisms, they have these little organelles in each of their cells that helps them generate the energy that they need to survive, which is to say, it takes sunlight and creates glucose, or energy. In the process of creating that glucose, inside the chloroplast, they have to be able to take light from the sun, and using a series of pigments, they have to be able to transform that light and capture the energy from that light in the most efficient means possible. And being that they're in the deep ocean, where there's very, very little light, very, very few photons that ever penetrate that far down in there, they need to be as efficient as humanly possible at generating energy using their pigment molecules within the chloroplast in order to survive. And somehow they use the phenomenon of quantum mechanics to achieve this, because there are a number of different ways you can transfer energy from one pigment to the next. Not all of those are the most efficient, and yet somehow within the chloroplast, those subatomic particles of energy are somehow transferred in a chain or in a trajectory or in a process that really is the most efficient, and it always ends up doing it all the time. And the only way they're able to do that is through the notion that quantum particles can almost act like octopuses, to where they can almost feel out the different scenarios that they can go in, and then all of a sudden choose one of those scenarios that is the most efficient and use that particular route. Where it almost seems like they're taking 10 different options, all 10 different routes, and yet they choose the most efficient route to the end goal. It's crazy.
It's really well shown in some of the experiments, like the double slit experiment, where you shoot photons at a target one at a time, and it ends up that the photons interfere with themselves to form this pattern in the background. And the only way to do that is if the photon took more than one path to get to its destination and interfered with itself. So it's a weird phenomena like that in quantum physics do happen. And I wish I was qualified enough to actually explain some of this stuff, but I am not, so I'm not even going to try. But what you're saying sounds crazy, but is actually real.
Well, it's just a product of the nature of quantum particles that they act both as a particle and a wave,
Correct.
Which is to say, as a wave, they can test out a number of different possibilities, and yet somehow all of a sudden choose to act on one possibility as a particle, which is bizarre.
Yeah.
Huh.
There is also, since we're just informing people, one other thing that they may want to look into other than quantum mechanics is something called Bohmian mechanics. And although it's not supported by many people, it is a theory that's alternate to quantum mechanics, and it gets rid of some of that uncertainty in quantum mechanics. But it's got its own issues and problems that it doesn't explain, but that could be because it's not developed well enough. But if somebody wants to look at Bohmian mechanics, they can.
There are other alternatives to try to, figure all this stuff out. There's still some people who are hopeful about string theory. I gave that up years ago. I think it has its uses, but I really don't think that fundamentally it's going to be of any real value or use, even if true. I mean, think about it. Okay, the universe is made of strings, so therefore what? I mean, what do we do with that information? I mean, don't get me wrong. Obviously, if true, we should figure it out, because I'd rather know it than not. And I'm sure it would have some use. The mathematics is really the only thing that's been plucked from that tree. The mathematics behind it is very beautiful and ridiculously over my head. I couldn't possibly fathom trying to comprehend that, really. It's ridiculous. The sheer amount of time and energy spent trying to make this theory work is mind-boggling, and it shows.
They're working towards actually making some predictions that are testable. I mean, so far that's one of the problems with string theory, is that the predictions that they make are not testable. And if I'm not mistaken, in order to probe physics on the scale of, to even get close to probing physics on the scale where you can maybe discern some of these strings, I think you have to have a particle accelerator that's as big as like the orbit of Pluto or something like that. I mean, you have to have an instrument that's ridiculously large. So it's just impossible to probe some of the stuff they want to probe to prove their theory. But I think they're making some predictions now that are somewhat testable, although probably not in any near future.
So, I guess one thing that we can kind of discuss along these lines is it is okay for the science to change, and it does change, and it will change. It's a good thing that it does change. But one of the reasons why, one of the excuses, rather, I'm going to use that word, one of the excuses that a lot of religious folk or just plain ignorant folk try to utilize is this idea that because it changes, that it's not reliable. And sometimes it's really hard to beat down that there are certain fundamental principles of the universe that aren't going to change. I mean, for example, gravity is not going anywhere. Nobody can deny gravity. That's not something that's ever really going going to change. How it works, what it actually is, rather, is subject to change. But the fact that it's there isn't. It's undeniable. I think one of the problems is a lot of people don't really appreciate how profound some of this stuff is. I mean, before we discovered we revolve around the sun, somebody looked up and realized that dark space on the moon is the Earth's shadow. Until somebody actually figured that out, there was a lot of myth and lore and legend or religious this, that, and another to explain that. I'm sure some people guessed that it might have been the Earth's shadow, but a lot of people made up a lot of weird stuff to explain that. It didn't really make sense to a lot of people that, the sun was moving around the Earth in a day, but that shadow didn't really seem to move much over the course of a month. So, deducing that it was the Earth's shadow took some time, and this was a relatively recent development.
I made a note of that before the show, thinking that may be an interesting thing to note. Copernicus actually was the first person to break the view out there that the Earth was the center of the universe. So what Copernicus said was that we in fact orbit the sun, and that was in 1543. So breaking kind of he established the heliocentric model where the sun is in the center, where before it was like an Earth-centric model. So I mean, the science is actually accelerating. In 1543, we discovered that, well, wait a minute, we're actually orbiting the sun. Then in the 1920s, Hubble discovered that, wait a minute, this is not the only galaxy. Then, it wasn't until 1998 that we discovered that the universe is expanding at an accelerating rate. So, yes. all these discoveries are coming in. And, one thing that I wanted to comment was, I've heard that same thing that we're talking about so often brought up, that, well, science is unreliable because it constantly changes. It's not so much that science changes, it's that we develop better technology, we develop better methods to make measurements. Mm-hmm. And those measurements will inevitably modify our theories and our understanding of reality. I mean, if you look at the experiments that Newton made and the explanations that Newton did for gravity and all that, those things are still true. I mean, on the scale of the solar system, you can easily use Newton's equations, and you'll come up with some pretty good answers. Especially on like Earth size, like for calculating orbits of satellites and all that. You can do that with Newton's laws all day long. You're not going to have any problems. And that's the thing. The new science that comes out, it just modifies the old science, and it explains it better. And
here's a really good example.
Okay, go
ahead. Even after Copernicus discovered that we lived in a heliocentric universe, when he was able to give an experiment that showed this, even from that point on, the vast majority of astrophysicists would actually believe that these orbits were perfect circles, and very, very specifically perfect circles. There were some people that argued that there might be some unusual orbits, but that God worked in circles because circles are perfect in their mind. In the history of religious ideas, this was something that was going around at the time, that everything that God did was perfect, so therefore we have to find the most perfect way that God would have done these things. So they think that on matters of the unseen and in matters wherever possible, God worked in perfect circles. So for the longest time, it wasn't just because of that, but that was obviously a factor that halted progress on that. Anyone that brought it up, people would refute it. Instead of with science, they would say, no, God wouldn't do that. And most people would go along with that. So it was something that really impeded the science, because I don't want to suggest that there weren't people that tried to show that this wasn't at least always the case. But, you're absolutely right. So over the years, our understanding of this has changed because our measurements have changed. And same with Hubble. We can, kind of come full circle here. You were saying nebula literally translates to fuzzy thing.
Oh, yeah.
So, at the time, this wasn't that long ago. There are probably people alive today, I think, that lived in this world. I'm sure that they thought that we lived in a static universe and that we were the only galaxy, These sorts of things, these ideas were very common, and it really wasn't until Hubble that all that collapsed, and that was not that long ago. Again, these discoveries are profound. The moment they turned on the Large Hadron Collider, that was a profound moment in history. There are all sorts of moments. When the Wright brothers, they recorded themselves flying. That was a profound moment in history. When they blew up the A bomb, that was a profound moment. But there are other ones, and there are so many unsung heroes. It's unfortunate.
One of the things I'd like to emphasize is when we talk about change in science, it's really an unfortunate word to use the word change, because of the fact that I think V mentioned it's more modifying, and it really needs to be emphasized as a modification. And when I say modification, I mean when people talk about science changing all the time, we're not taking a 100-page document and lighting it on fire. That's not what we're doing in science. Okay, what we're doing is we're taking line 1081 on page 100 at the very bottom. We're just going to change a single sentence. That's how scientific change occurs, is a single sentence in a 100-page document. That's not changing everything, starting from scratch. That is modifying a very, 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 very slight tweak to what we currently know. Therefore, things like gravity, things like evolution, they're not going anywhere. They're going to be there forever. They might be slightly, ever so slightly tweaked at the amount of fractions of a percent, but that's it.
Yeah. No, that's an excellent point. I'm glad that you brought that up, because I never actually thought about that particular point, using the word modified as opposed to changed. And I thank you for that. That's actually really good. There's a lot of language problems out there as well that really propagate this process, this misunderstanding of science. I'm not going to say I'm perfect. Obviously, I should have used the word modified, and I will in the future. But there are things that really that are kind of misleading, like the word observer. Even that tends to imply that there has to be some conscious thing looking at a thing, or is looking at a thing. Observer does not mean that when we're talking about physics and an observer in physics, what we're talking about is a thing, a physical thing that exists, is an observer in our universe, in this realm. So when Einstein is talking about one observer over here going one speed and one observer over here going another, they don't have to be people for these effects to be real. Okay, consciousness does not dictate the laws of reality. These are just things in these models. And it's one of the things that really gets in the way of understanding the science.
We should just teach science better, I think, to kids. I'm currently reading Richard Feynman's book. I know you guys probably heard of Feynman. He's one of the most famous scientists. And, one thing that he was talking about, he was for 1 or 2 semesters in Brazil, and he was teaching in a college there. And one thing that he noticed was that the students in that college, they were very good students. They could memorize anything you gave them. He would ask them questions, and they would recite stuff out of the book line for line, but they had no understanding as to what that stuff meant. And at the end of that year that he was there, or semester, he gave this big speech in front of all these professors, and he basically flat out told them in their face that in Brazil at the time, this was in the 60s, I believe, or 50s or 60s, they weren't teaching physics. People are just memorizing things, and that they weren't teaching science. And so what we should just do is teach kids the science, explain to them what we mean when we talk about different things and what we mean by observer. How do we find out that this law works this way or that way? We should teach them the scientific method and go from there. But just in general, the way science is taught in the U.S. is, especially in the high school level, it's absolutely ridiculous in my opinion, and needs to be very much improved.
All right, guys. Well, on that note, we are running out of time. So I just want to thank everybody for listening. I want to thank you guys for being on the show. And we'll catch you guys next time.
That is all the time we have for you this week. This has been the Hoosier Humanist Hour. Be sure to check out FreeThought Fort Wayne on Facebook and on meetup.com. Thank you for listening, and we hope your days are filled with logic, reasoning, and the eternal quest for knowledge.
From there.